Hola, soy David Montemayor,
Domo, ore wa Logan desu.
and this is our crash course on
Nuclear engineering!
Okay, talk about nuclear related stuff. They always think about nukes.
Boom!
There is much more than that, than just blowing up things around the world. Nuclear technology has been around for more than half a century, and it is becoming more and more popular. 37 countries around the world have nuclear power sources. The nuclear energy innovator, France, generates 80% of its energy from nuclear powers, and it remains as the lowest greenhouse gases emitter in the world. Nuclear energy in general produces a negligible number of CO2 and greenhouse gases. So, how does it work?
Nuclear power generation is actually a lot more complicated than what it usually seems. Multidisciplinary collaboration is needed to install such a system. Let's simply talk about the nuclear fuel cycle. The cycle begins with mining, which is a typical way of gaining a lot of resources. So what we actually look for is this kind of green rock called uranium. It's extracted from the ground and it's mainly found in Canada, Australia, and Kazakhstan. This first stage of the cycle is one of the dirtiest ones and releases loads of chemical into the atmosphere.
After mining, uranium ore is milled, and yellow cake
U-308
is produced.
Yeah, it actually looks like a cake.
This is followed by the conversion of yellow cake into UF6 gas through a chemical process. Uranium found in nature is made up of 99.3% U-238 and 0.7% U-235. We want U-235 because it is a fissile isotope. This means that uranium-235 can spontaneously experience fission. We enrich uranium to increase the concentration of U-235 from 0.7% to around 3.3 to 5%. This is achieved because of the isotopic difference in mass that allows us to separate U-235 and U-238 through centrifuge or diffusion.
After the enrichment, we chemically process uranium into UO2. This is compressed into pellets that are zirconium coated. Then we put these pellets into long tubes called fuel rods, grouping to fuel assemblies, and assembled into a reactor core. The reactor core usually consists of 17 by 17 grid that holds around 20 control rods,
which we will later talk about,
one sensor, and 150 to 200 fuel assemblies. This whole process altogether is known as the front side of the nuclear cycle. So, you must be asking yourself by now, where does the energy come from?
Most energy production in general comes from the turning of a turbine by means of steam. In a nuclear reaction, we use fission processes to heat water which vaporizes and condenses to form a cycle that drives the turbine. The nuclear reaction that occurs inside the nuclear core is called fission. Fission is the splitting of an atomic nucleus into two or more daughter products. This is achieved by bombarding the nucleus with a neutron. Upon splitting, energy is released as well as 3 additional neutrons. But wait a second, where does the energy come from?
Acknowledge Albert Einstein, his famous equation, E equals mc squared.
AKA, the mass energy equivalence.
What the periodic table doesn't tell you is that the mass of the proton and the mass of the neutron is not exactly 1 AMU. Supposedly, U-235 has 92 protons and 143 neutrons. The mass of U-235 is 235.043999, which should equal to 1.0086 times 143 neutrons plus 1.0072 times 92 protons. But this will result into 236.8922 AMU. So what is going on? There is something called the binding energy that refers to the strong nuclear force.
The strongest force of the 4 forces found in nature,
Which binds the nucleons
protons and neutrons.
tightly together. Because these forces remove some of the energy, the daughter products of a fission reaction, which have less of these forces, have an overall greater mass. This is called the mass defect. Coming back to the fission reaction, what can we do with these additional neutrons?
3 neutrons created continue interacting with more isotopes. They ignite a chain reaction that goes on and on. This is how we achieve sustained power generation from nuclear sources. However, not all neutrons are picked up by uranium-235. They are just so popular that everything can potentially stray them off from their intended destination. They can be absorbed by another source like uranium-238, the moderator, or the coolant.
We'll talk about them later on.
The neutrons can also escape from the system and just never return for any useful purpose. This is called leakage.
Into something called the multiplication factor,
aka the K value.
It is defined as the ratio of neutrons produced versus neutrons lost in the system reactor core. There are three conditions. 1. Supercritical. K is greater than 1. 2. Critical. K equals to 1. 3. Subcritical. K is less than 1. Essentially, as time progresses, the reactor tends to rise to supercritical levels due to increasing energy levels. The worst case scenario could result in the meltdown of the reactor core. In a critical level, the reaction remains constant and we get a steady generation of energy. That's all we want. If the reactor is subcritical, we slowly lose neutrons. The chain reaction cannot be sustained, so the system eventually shut down.
Many ways we can artificially alter this K value. The most common one is the usage of control rods. They are hungry neutron absorbers that can be used to control and moderate the K value. Right after fission reaction, the resulting neutrons are released at a very high energy level. They are said to have a low cross-section.
Probability of interaction.
We want to bring neutrons down into a lower energy state where they have a higher cross-section. We achieve this by slowing the neutrons down with a moderator in the subatomic level. The neutrons collide with other nuclei in inelastic collisions where some of the energy is transferred to the moderator, and thus slowing the neutrons down. We also need to worry about the temperature levels inside the reactor core. The heating up of the core will cause fuel rods to melt down and release dangerous chemicals and radioisotopes into the building. Therefore, we pump coolants to maintain a certain temperature and operate backup pumps during emergencies and accidents. So, now that we know and understand what happens inside reactors, let's talk a little bit about commercial reactors operating around the world.
Sustained nuclear chain reaction dates all the way back to 1942, when the Chicago Power 1 achieved the first nuclear chain reaction. This prototype was adopted and improved by Admiral Hyman G. Rickover for the use in submarines for the Navy. The first commercial nuclear power plant was established and located in Shippingport, Pennsylvania, which began to operate in 1957. Commercial reactors have been divided into specific groups, namely Gen 1, 2, 3, 3+, and 4 reactors. The most common Gen 2 reactors running around in the commercial world picked up Rickover's design. These plants are light water,
H2O,
moderated and cooled. The two main types are boiling water reactors,
BWR,
and pressurized water reactors.
PWR.
Gen 3+ have passive safety mechanism that protects the plant in the case of an accident without any human interference. Gen 4 reactors are developing conceptual design including the fast neutron reactor, molten salt reactor, sodium-cooled fast reactor, very high temperature fast reactor, etc. These are in the design stage, but they might come about in a few decades.
We enter the nuclear fuel cycle and step into its back end. After fuels are depleted, they are cataloged as spent fuel. Spent fuel is made up of various isotopes, and they are radioactive. The fuel is later placed in cooling pools because the radioisotopes remain hot due to radioactive decay. From now on, there are three things we can do with the fuel. 1. Throw it away. 2. Recycle useful materials and reprocess it. 3. Do nothing with it.
Believe it or not, this is the most popular choice.
Some of the spent fuel is recycled and reprocessed, and the leftovers are called high-level fuel, or waste. The back end of the fuel cycle is very controversial and dangerous. High-level wastes contain radioactive elements that emit radiation and can endanger humans and the environment. Since many of these radioactive isotopes take millions to billions of years to decay, they will not only affect us today, but also hundreds of generations after us. Throughout the past decade, there have been many waste disposal techniques proposed. Still, no completely efficient way of disposing fuel has been found. So, let me dive into a few of the solutions that have been proposed throughout the years. 1. Shoot waste into space, because why not?
Shuttle Atlantis to assemble the framework for the science laboratories of tomorrow.
2. Inject it into the underground water tunnels and wells. Not a very good idea. 3. Dig up a very deep hole and throw everything into the ground. 4. Throw it into volcanoes because it should burn up theoretically. 5. Transport waste onto a remote island and just leave it there, no man's land. 6. Place it into the underground seabeds. Screw the fishes, they're like fish. 7. Transportation processes. We have mostly adopted the solution of burying nuclear waste in geological repository, which is a very deep hole. The most famous of all is Yucca Mountain, an incomplete project that costs up to $13 billion already.
But that is a whole other story.
However, because Yucca Mountain has been shut down and there are very few repository sites, we simply place the waste in dry casks or poles, and these are called interim storage methods that are not permanent solution and only last about 100 years. Transmutation is the most promising waste disposal technique that has been proposed. If you remember, it was the 7th option. It consists of reducing the half-life of radioactive isotope. This way, we would only have to worry about them for a shorter period of time. Transmutation hasn't been fully developed, but it is something that could be achieved in the near future.
Technology is evolving, and scientists are perfecting the methods of energy production. One interesting idea that is being tested and developed is the implementation of fusion reactions rather than fission ones. Unlike fission, fusion is the joining of atomic nuclei to form one nucleus. This reaction yields far more energy than fission. Still, it is very complicated to produce a confined reaction. To sum it all up, nuclear energy brings a panorama of infinite possibilities. It is a sustainable source of energy that can power our world in the future. However, as everything, it has its problems. Radiation from waste, nuclear accidents such as 3 Mile Island, Fukushima, and Chernobyl, and the proliferation of nuclear weapons are all problems that have to be dealt with. New technology and research is helping scientists make nuclear energy completely clean and safe.
During this video, you have learned about
The nuclear fuel cycle,
fission and nuclear reactors,
types of nuclear reactors,
nuclear waste,
fusion,
and the future of nuclear technology.
Thank you for watching this episode of Nuclear Engineering.
Sayonara!
Hasta la próxima.